Picture a fully constructed, operational nuclear power plant, far from the sea. Islands of steel gleam under spotlights. Reactors work silently within concrete shells. Now for the catch. It never happened. Not a single what reached a single home. It was an idea that virtually rewrote the way nations generate energy. Born of ambition, then swallowed by reality. America in the early 1970s felt electric, literally and politically. Nuclear power was the future everyone wanted to believe in. Cities were growing fast. Demand for electricity climbed year after year, with no ceiling in sight. Utility executives spoke of an electric economy, a world where clean, endless power would replace coal and oil entirely. Nuclear plants seemed like the answer, but building them on land had become a nightmare. Every site fought its own battle. Local communities protested. Regulators slowed approvals. Rivers and lakes strained under the heat these plants dumped into them. One utility, Public Service Electric and Gas of New Jersey, looked at the coastline and saw something different. Open water, far from angry neighbors, far from environmental limits. In 1971, PSE&G partnered with Westinghouse to imagine reactors built not on concrete foundations, but on steel platforms, floating just off the Atlantic coast. A year later, Offshore Power Systems was born, a joint venture between Westinghouse and Tenneco's shipbuilding arm. Engineers pictured reactors assembled like ships on an assembly line, then towed out to sea. It felt less like construction and more like science fiction turning into policy. The idea carried real weight. PSE&G signed contracts for 2 reactors in 1972, then 2 more in 1973. Jacksonville, Florida became the staging ground, a shipyard reborn as a nuclear factory. For a brief window, this looked inevitable. Engineers believed they had solved land's oldest problems: space, water, and public resistance. What nobody fully grasped yet was how fragile that confidence really was. The vision was beautiful on paper. History, though, rarely follows the blueprint. Behind the drawings stood real people. Engineers who had built ships now designed reactors. Executives staked careers on a concept nobody had tried at this scale. Investors watched cautiously, weighing risk against reward. There was pride in the room too, a sense of American industry solving a problem the old way couldn't. Newspapers ran illustrations of glowing platforms at sea, half factory, half fortress. It was optimism dressed in steel and concrete. Nobody yet knew the ocean, the economy, and public opinion would all push back at once. Nuclear power had an image problem long before this project began. By the early 1970s, public trust was already cracking. Local communities didn't want reactors near their homes, their schools, their water supplies. This resistance had a name. Not in my backyard. Land-based projects faced lawsuits, hearings, and years of appeals before a single foundation was poured. Offshore Power Systems saw a loophole in geography itself. Push the reactor miles out to sea, past the horizon, past complaint range, and maybe opposition would fade with distance. The plan targeted a site off Little Egg Inlet, New Jersey, nearly 3 miles from shore. Out of sight seemed to mean out of mind. But the strategy had a blind spot. Opposition didn't stay offshore. It followed the project back to land, right into Jacksonville, where the shipyard itself became a target. Residents worried about radioactive materials moving through their city before ever reaching open water. Fishing communities near the proposed site in New Jersey raised their own alarms, fearing disrupted waters and damaged livelihoods. Coastal resort towns worried about their image, about tourists avoiding beaches near a nuclear neighbor. Distance from the shoreline hadn't erased the fear. It had simply relocated it to a different coastline, a different set of neighbors, a different fight altogether. Regulators added their own layer of friction. New environmental laws now demanded detailed impact studies before any federal license could move forward. Every hearing invited fresh objections, fresh delays, fresh uncertainty. Utility executives had hoped the ocean would remove politics from the equation. The company found itself defending a technology in 2 places at once, on a shipyard floor and inside a courtroom. Neither audience was fully convinced. A nuclear reactor needs one thing above all else: constant cooling. Without it, heat builds fast and safety margins shrink. Land-based plants usually pulled that cooling from rivers or lakes, finite sources with real limits. Droughts lowered water levels. Summer heat raised river temperatures past safe thresholds. Regulators worried about thermal pollution, about fish kills, about ecosystems stressed by warm discharge water. Public service electric and gas had already faced this exact fight on land. Communities furious over warmed rivers and dying wildlife nearby. The ocean offered something rivers simply couldn't: near limitless volume. Out past the breakwater, cold seawater could flow in continuously, absorb heat, then return diluted into an enormous body of water. The engineering plan called for roughly 2,000 cubic feet of circulating water per second, feeding each reactor pair. That number sounds abstract until you picture it. Enough flow to make thermal limits almost irrelevant. Discharge points were positioned carefully too, designed to avoid pulling warmed water back into the intake, and to reduce fish entrapment near the plant. On land, engineers fought physics and geography at once. At sea, physics simply cooperated. This wasn't just a technical convenience. It was a genuine advantage no coastal or inland site could match. One clean escape from a problem that had haunted the entire industry for years. For PSE&G, this single factor justified enormous engineering risk elsewhere in the design. Solve cooling permanently, and half the industry's oldest headaches disappear overnight. There was a psychological benefit too, one rarely mentioned in technical reports. Land-based utilities constantly negotiated with state agencies over water rights, discharge permits, seasonal restrictions. Those negotiations could stretch for years, tangled in bureaucracy far removed from engineering itself. An ocean site sidestepped much of that entirely, since federal waters operated under different rules than inland rivers. Engineers could design around a stable, predictable heat sink instead of chasing shifting environmental thresholds year after year. Confidence grew inside the project because of this. Open ocean doesn't negotiate. Hurricanes, rogue waves, even the risk of a stray tanker collision, all threatened a floating reactor in ways no land site ever faced. The design had to survive waves reported near 43 feet, alongside sustained hurricane winds over 150 miles per hour. To meet that threat, engineers planned a breakwater described, at the time, as the largest and strongest structure ever proposed for the open sea. Concrete caissons would be sunk first, then filled with sand and gravel, forming an artificial reef around the entire site. On top of that reef came the real defense, thousands of interlocking concrete units called dolosse, shaped roughly like oversized jacks from a child's game. Sources vary on the exact count and weight, ranging from roughly 17,000 to 70,000 units, with individual pieces weighing anywhere from 11 tons up to 80 tons each. Even at the lower estimate, this was concrete on an almost unimaginable scale. Each dolosse interlocked with its neighbors, breaking wave energy before it ever reached the platforms inside. The goal wasn't just calm water. It was creating a fortress capable of shrugging off nature's worst tantrums while 2 live reactors floated quietly at its center. Building this breakwater alone was projected to take roughly 4 years per plant, before the reactor platform ever arrived. Cranes would place caissons with almost surgical precision, working against tides, weather windows, and shifting seabed conditions. Every dolosse had to interlock correctly, or the entire wave-breaking effect could fail under real storm pressure. Engineers also accounted for a pre-existing sand formation near the New Jersey site. Even so, the sheer volume of concrete involved dwarfed almost any coastal defense project attempted before it. None of this collapsed because the engineering failed. It collapsed because the ground underneath the entire industry shifted. The 1973 oil crisis sent shockwaves through global energy markets almost overnight. Electricity demand, once assumed to climb forever, suddenly flattened across the United States. Utilities that had planned for endless growth now faced a very different reality. Interest rates climbed sharply, making massive upfront capital projects far riskier to finance. Nuclear safety regulations kept tightening too, adding cost and complexity at every stage of design and review. A technology this unproven, this capital-intensive, needed exactly the kind of economic stability the mid-1970s simply refused to offer. Confidence, once the project's greatest asset, evaporated alongside the demand projections that had justified it in the first place.